All right, so we're going to take a look at an example here of viscous forces acting on a plate. So the plate is going to be skimming along a water layer. The water layer is 3 millimeters thick, so thin lubricating water layer, and we have a steady velocity of 0.6 meters per second for that top plate. And the question being asked to find is what is the force required? Find force required to keep the plate moving at 0.6 meters per second. So at this point, if you want to stop the video and see if you can figure it out, that'd be fine. I'll just keep going with this right now, so people who want to just watch can. Or you can try it yourself and then see if you can get the solution. So we're going to need to know some things. We know this is going to be a problem involving shear stress and viscous effects. We know that the force is going to be related to the shear stress with this relationship. So we're going to have clearly a force on the plate, shear stress on the plate that is caused by the fluid in the x direction, due to fluid that's in the y direction. So I guess we should put some x's and y's in here. There's a y, and this will be an x down here. So we have some x and y direction. But anyway, that's the force. And so it's going to be related to this shear stress. And then you're going to have to multiply that by the area, because the more surface area there is, the more force will be required. So that's the basic formula for calculating a force when you have a local shear stress, so exerted by the fluid. So in this case, we know A is 0.75 meters squared. So we don't need to worry about that. We just need to find that tau. And we know that water is a Newtonian fluid. So as a Newtonian fluid, the formula is going to be mu du dy. And mu, of course, is the dynamic viscosity of water. And we know that. We saw it in the last lecture that mu for 20 degrees C water was 0.001 kilograms meters per second. Now, of course, if you didn't know that, you would look it up in a book or you'd look it up online. Be careful of your units. And this is at 20 degrees Celsius. And we'll see that that really matters in the next lecture. So we've got a viscosity and we've got a temperature related to that. And we've got a way to calculate this force if we knew this. So if we knew du dy. Why is there a minus sign? Well, this is because we're looking at the top plate, and the top plate, this should be, the normal direction pointing into the fluid. So that's pointing in the negative y direction. So that gives us the negative sign because the direction of the fluid gradient that we're measuring is in the negative y direction. Okay, so we know actually the velocity profile for flow between plates when the plates are steadily moving. We said earlier that what happens when you have a steadily moving plate in a thin gap, you have a linear velocity profile. So we're going to have this same velocity profile we saw before. We're going to have u0 up here, we're going to have 0 down here, and it's going to be a linear profile. So that's what's going to happen because we haven't proven that yet, but we have learned that already. So velocity profile is linear for steady flow between plates. Well, I should say between one moving and one stationary plate. Right, so that's what we've got. We've got a linear velocity profile, and we've got one plate moving, one plate stationary. Top plate's moving at u0, 0.6 meters per second. Bottom plate sitting still. So that allows us to calculate du dy. So du dy is easy. It's simply du dy is equal to, because it's a plate, a linear profile, we have u of the plate minus 0 divided by the gap thickness. We saw this before. In this case, the u of the plate is 0.6 meters per second. Of course, 0 is still 0, and the gap thickness is now 3 millimeters. Obviously, you got to be careful with your units here. So you get 0.6 meters per second divided by 3 millimeters. and that equals 200 1/2 seconds. So we have 200 1/2 seconds is our du dy, and that allows us to calculate our tau. So our tau xy, that is the force exerted on the plate by the fluid. 0.001 kilograms meters second, that's our viscosity, times our 200 1/2 seconds. That gives us negative 0.2 kilograms meters per second squared. So that is that the force is being exerted on the fluid, by the fluid on the plate, is going to be pushing the plate backwards. That is trying to keep the plate from moving forward. Well, that makes sense, right? You're trying to push a plate along a surface of water. Obviously, you need to exert force forward in order to counteract this frictional drag, dragging the plate backward due to viscous effects. The force on the plate, the total force on the plate due to the water, is going to have to be the area times that tau. So that's equal to 0.75 meters squared, we said was the area, times the negative 0.2 kilograms per meter second squared. And you get all that, you get negative 0.15 kilograms meters per second squared. And that is the same as force on the plate is equal to negative 0.15 newtons. So that's the force on the plate. If you need to keep the plate going, you need to counteract that force. So you need to push the plate with the opposite of that. So that's a positive force of 0.15 newtons. The important thing here to note are two things. One is we can calculate this. That's great. Second thing is this is tiny. A newton is a really, really tiny force. So you're talking about a very, very light force to keep that plate moving across a surface of water. And that's actually why lubrication works. So when you have a frictional situation between two solid surfaces and you add oil to that, what you're doing is creating that very thin liquid layer, because that really, really reduces the friction a ton and causes things to move very, very easily. So that's the whole basis of lubrication, which is just one area of fluid mechanics.